Hi folks, welcome back. So this week what we're going to be doing is we're going to build ourselves a phaser. Now a phaser is a type of modulation effect, we call it, where basically we take an input signal and we take a copy of that input signal and we alter the phase of some of the frequency components of our copy, and then we mix it back in together, and those phase altered frequencies cancel out the frequencies in the original and we get a specific kind of sound. So originally this video was a part of another video which got too long, so I split that video into two videos. So I'm just going to do a little recap of that video now. So when we talk about phase shift, what we're really talking about is each component of any sound we can think of as a sine wave at that frequency. So when we talk about 20 Hz, 100 Hz, 2 kHz, whatever, we're talking about the sine wave at that frequency in that sound. And then we're talking about what the amplitude of that sine wave at that frequency is, and also what the phase of that frequency is. So when you add two sound sources together, so I've got two sounds, sound A and sound B, and I want to add them together, what you're really doing in a kind of frequency domain sense is you're taking each frequency from each sound, so 10 Hz and 10 Hz, and you're adding them together, and then you take 11 Hz and 11 Hz, and you add them together. 12 Hz and 12 Hz, and you add them together. So what the phase is telling us is how those two frequencies are going to add together. If the two sine waves look the same, so the peaks and the troughs line up, they'll add together. If they look a mirror image of one another, so the troughs line up with the peaks, then they'll cancel each other out. When they're mirror images of one another, we say that one is 180 degrees out of phase with the other. That's because sine waves are rotations, and so a half a rotation around is 180 degrees, a full rotation is 360 degrees, so you can shift in phase all the way from 0 degrees round to 360 degrees, where you end up where you started. What we looked at last time circuit wise was how we can take the humble inverting amplifier in this configuration, and by adding a few cleverly placed resistors like this, then we can take advantage of the negative feedback of the inverting amplifier. Okay then, so I'm just going to quickly go over this circuit in a simulation, which I'll include in the description, just so that we're definitely all on the same page. So we've got the input signal here, output signal here, and this is the signal that we're putting on the inverting input. So the takeaway of this circuit is that the input comes in and gets mixed here with the output through this negative feedback. So what the output will do is make sure that when the feedback is mixed with the input, that those two signals mix to make the same voltage that we've put on the inverting input. So here I've got the potentiometer all the way up, so I'm just putting the input fully on the non-inverting input, and so the output is just putting the same voltage here. So this is just a follower, look. If I remove this resistor, it's exactly the same operation as a follower. So now if I ground this, so you can see now the feedback is just the opposite signal to the input, so that when the two signals mix here, they make ground. And that's how this circuit works in a nutshell, and we can vary that all the way in between fully inverted and fully following continuously. So that's what my last video was about basically, and so what we're going to do this time is see what happens when we phase alter this signal as well as attenuate it, and see how we can take advantage of that to make ourselves a phaser. So there's a link to my last video in the corner if you want to know more about this circuit, but if you understand that fully, then you can carry on with this video. So now we're going to take this concept of the inverting amplifier that we've been exploiting and extend it even further by adding in phase shifting components and seeing how that changes the circuit. And it's another simple alteration. All we need to do is add one component and shift some things around a little bit. Now instead of just putting the input straight onto the non-inverting input, we're now putting it through, this is essentially a phase shifting network. So this potentiometer controls the amount of phase shift by controlling the current through this capacitor, which sets how quickly the capacitor charges, which decides how phase shifted the signal is. Check out my capacitors explained videos if you want to know more about that. And also at the same time sets how much of that phase shifted version of the input signal appears at this input, and then through the op-amp feedback, the output will output what it needs to mix with the input to create this signal. So it's kind of interesting and weird and complex and maybe a little bit confusing, but let's go upstairs and have a look at it on the oscilloscope, and hopefully it'll make a lot more sense. Okay, so we're back upstairs. We've basically just added a capacitor in, as I explained downstairs. So let's have a look at the oscilloscope here, where we've got the input signal in yellow and the output of the op-amp in purple. And as I turn the potentiometer, we can see that the output shifts in phase. And so we can vary this from in phase, like this, to out of phase. And so how is this working? Well, it's very similar to how the last circuit was working, in fact. And if we put channel 2 on here, we're seeing the yellow signal is the input signal, and the blue signal is what we're feeding onto the non-inverting input. As I vary this resistor, the phase and the amount of the signal that I feed through changes. So that blue signal is what we're putting on the non-inverting input. And so that's the output fully in phase with the input. And that's the output fully out of phase with the input, which again is just grounding that input. So now we remember that what comes out of the output is just what is required to be added to the input signal to make that blue signal on the non-inverting input. So we can see when it's here, the op amp just figures out that this sine wave is what we need to add to this sine wave to get this sine wave. Okay, so let me just explain how these sine waves add together without going into the maths of it. I'm just going to show you graphically how we add sine waves. So this is a sine wave, and this yellow arrow represents that sine wave. How long the arrow is how loud the sine wave is, and the angle from the x-axis is the phase of that sine wave. So here's another one. You see how the phases are 90 degrees apart and the two arrows are 90 degrees apart. So we add these together by just taking one arrow, sticking it on the end of the other, and drawing a line to the end of the second arrow like this. Okay, so that's how you add sine waves together. It's kind of weird. So let's just pick two other random sine waves and let's add them together. Okay, same way, same method. So what we can see here is quite useful, which is that when the two sine waves are the same amplitude, so the two arrows are the same size, generally speaking, the phase is going to be the average of the two sine waves. So that's a handy thing to remember. So now let's see what this sine wave looks like. Okay, because we can go the other way and we can turn these phasor arrows into sine waves. So let's do that now. So that one goes down there like this. So what we've got here is this yellow plus this blue equals this purple. And so not just changing the phase, but changing the amplitude of one of the signals can change the phase. Like this. We see how all we've done is make the blue amplitude smaller and the phase of the purple wave shifted. This is a simplified version of what this circuit is doing. We're altering the amplitude and the phase of one of our signals, and by doing that we can keep the purple signal constant in amplitude and only changing in phase. Okay, so how is all this phase shifting happening in our circuit? Let's have a look on the whiteboard. Let's take a simplified version of the circuit that we're working on, which looks something like this. Okay, so what we've essentially got here is we've got our input signal coming in, going through some RC stuff, and then we've got an inverting configuration coming back. Now how I want us to think about this network is as a phase shift network, and the reason why I'm going to explain it to you like this is because this is something that we use a lot in op-amp circuits, and something that as we go on to oscillators we're going to see a lot more, and that is that we can kind of think of a resistor and a capacitor in parallel like this as a kind of high pass filter and a low pass filter put on top of one another. And how we're going to think about that is we're going to think about it in this configuration. Remember, in electronics we can take any point that we want at ground and we can analyze any point that we want relative to that ground. And the circuit will look quite different depending on how we do that, and we can do this thing called superposition. When we're using linear components like resistors and capacitors, we can just add those responses up and the total response of the system will be the sum of those responses, and that will make sense in a second if that's a load of jargon. So if we look at this like this, if we take V2 here to be ground, then that looks like this. Looks like a low pass filter that we've seen before. And conversely, if we take V1 to be ground, okay, and this looks like a high pass filter. What I'm going to do is I'm going to draw the frequency and phase response of the low pass filter, high pass filter, and then the sum of those responses, and then hopefully you'll see what's going on with this phase response. So this is the low pass filter, this is the high pass filter, so this is the amplitude response. Right, so this is frequency going up this way. Right, so these are low frequencies, these are high frequencies, And so we know low pass filters, there's no attenuation at low frequencies. That's what this straight line means. All right, so this is where the attenuation has gone down by 3 dB. We call this the 3 dB point, and then the attenuation increases as we go here. So same capacitor, same resistor, just in a different configuration. We have the same 3 dB point. So at this point, the output is 3 dB below all the way up here at high frequencies, and we have the opposite effect. And so kind of intuitively, hopefully, if we add these two responses together, they're just mirror images of each other, so they just add up to give you a consistent output, and that's what we saw in the circuit. The output doesn't drop as you change the phase, but the phase response is a little bit different. Okay, so as always, you'll have to forgive me for my average drawing skills, but the important thing here is that the phase shifts as we increase in frequency. But what we can see here that makes things a little bit more complicated, and this is why I didn't want to go into the maths, but I think graphically it's quite straightforward to understand. So what we've got here is 0 degrees, minus 45 degrees at the 3 dB point, and minus 90 degrees all the way up here. So that's for the low pass filter. For the high pass filter, at low frequencies down here, we start at minus 90, and then the phase shift increases to minus 180. Okay? But what we can see here is because the amplitudes change with frequency as well, there's only one place, which is the 3 dB point, where the numbers add up in a way that makes sense intuitively. So we've got minus 45 degrees here, and this is actually minus 135 degrees here. Minus 45 plus minus 135 gives us minus 90 at the 3 dB point. Okay, and all I'll tell you from here is that because the amplitudes are all different at every other point, so these amplitudes are the same, at every other point the amplitudes are all different, it's not so straightforward to work out how these add up, but essentially the phase response goes from 0 to 180 to minus 180 with a similar looking curve to this. But a curve that passes through minus 90 at the 3 dB point here, and it has a constant amplitude. And so what we can see is that as we increase in frequency, we shift more and more high frequencies until up at the high frequencies here, we've got quite a lot of high frequency information shifted up and around this 180 degree mark. And as we spoke about earlier, 180 degrees is the point at which you start to get phase cancellation, and you're going to have those frequency contents cancelling one another out. I've built the circuit up a little bit more. As with every video, I will have schematics down in the description. What I've done here is I've added some voltage control. This is a JFET, and these are just a couple of resistors. And what these are doing is they're basically acting as a voltage controlled resistor. So I've got some control voltage here, which is coming in through this resistor, and it's just, the JFET is kind of like a diode. If you imagine it as a neck of semiconductor material that kind of opens and closes like this, and it changes its resistance as it does it. I'll go into more detail in another video, and you'll have schematics in the description if you don't know what I'm on about. But basically I've just got a little bit of voltage control down here, and this is just that same circuit that we had a second ago. And so I'm feeding this up here, and this bit here is just an inverting amplifier, and then I've got a mixer up here where I'm just mixing in the phasor signal with my original signal. So let's have a listen to what that sounds like. I've made just like a simple loop so that I don't get copyright striked. So let's just have a listen. That was one stage of this kind of phasor that we've been working on. It kind of sounded more like a filter. So as the higher frequencies are pushed 180 degrees out of phase and then mixed in with the original, they cancel out, and that gives the effect of that kind of low pass coming in and out. Now that sounds nice, but it's not really what I think most of us think of when we think of a phasor. While that is phase cancellation going on, the kind of typical phasor sound is more of that kind of swooshing sound that we all know. You'll know it when you hear it, and I'll show you it in 1 second. And so the problem here is what's going on is that our phasor isn't selective enough. What's happening is we're kind of pushing all of the high frequencies out of phase and mixing them in, and so that's kind of cancelling out too much stuff. So if we come back to these graphs that we were talking about earlier, if we can be clever about this and think we know that there's 90 degrees phase shift only at this very specific frequency at the 3 dB point, which is also conveniently very easy to calculate because it's just when these two impedances are the same. Or if you just like a simple equation, it's 1 over 2 pi the resistor times the capacitor value will give you that 3 dB point. So we know that at this frequency there's exactly 90 degrees phase shift. So if we simply cascade 2 stages of our op-amp phase shifter, then we can control very easily a very specific frequency. So you can see how this phase changes quite rapidly around here. So instead of having all these high frequencies cancelling out all at once, we've only got a much narrower range of frequencies here cancelling out, because obviously 90 degrees times 2 is 180, and these high frequencies that are shifted 180 degrees will be shifted 180 degrees and then 180 degrees again, which goes to 360, which means they're back around here very much in phase. So we've really only got a very narrow window of frequencies that are being shifted into that phase cancellation area, and we can take advantage of that. So what I've got here now is I've got 2 stages of that phaser. So I've got one stage here, and then I've got the output here coming through this white and then black wires chained into the input of a second stage. And so what that's going to do is push only this frequencies around the 3 dB point will be shifted 180 degrees out of phase, and we'll get a tight notch in the frequency response, and that frequency response we can move around by varying this variable resistor. And that second stage is then coming out through this green wire, and I've just got this amplifier stuff from my previous video. You don't need this explicitly, you could go straight from the output of the phaser up to this mixer and then just mix in the phases signal with your original signal, which I've got coming in through this blue wire. So let's have a listen to this now and see how it sounds compared to last time. Okay, so as we can see there, we've definitely got some phasing stuff going on. So let me just show you kind of a few of the things that we can do with this circuit. So one of the things that you'll notice is I've got this extra bit up here which I've not spoken about, and what that's doing is that's actually giving us some feedback. With this grey cable, what I'm going to do is I'm going to take through this potentiometer some of the output of the second stage, and I'm just going to feed it through this potentiometer, and then with this yellow cable I'm tapping it off. And I've just got, this is one of those phase flipping circuits from last video, so I can alter the phase of the feedback, and then I'm just feeding it into what I've got here is just a buffer, and then this buffer going through a 10k potentiometer back into the input of the phaser. So the phaser has a loop that goes from the output of the second stage back into the first stage. And so what that will do is I can turn this pot and basically feed back more signal, and that will make the phasing deeper. I can also take the feedback and I can put it into the input of the second half, and that gives you a different kind of sound. And obviously the more stages you have, you can put the feedback at a different place. So if you have 4 instances of this little phase shifting circuit, that will give you 2 notches in the frequency response, remember. You also then have 4 different places you can put the feedback back into, and that will give you a different sound. And you don't have to do this with the phase inversion stuff. It can be as simple as just, if I just remove this, I can just take this 10k resistor and take it from the output and feed it back into the input here. So the only thing you have to think about with these feedback resistors is that you have to be careful how much of the signal you're feeding back, because you can, by adding feedback, you're decreasing the stability of your circuit. Right, so you might get some howling, it might break it completely, not permanently, but it might, you know, go all weird on you. So see there, for example, that was way too much feedback. I fed back the same, because I'm using a 10k resistor here, I'm feeding back the same ratio. So I'm basically feeding 100% of my signal back. If I get a bit of a bigger resistor, like maybe a 22k, so listen to what happens as I add this feedback resistor. not only is it deepening the phasing, it's also changing the frequency response. It's exaggerating some frequencies, which gives it a kind of mid-range ear sound, which is quite nice. So experiment with feedback, experiment with different values for your phase shifting networks as well. And now obviously the final thing that you could do, you can add an extra 2 stages, and what that's going to do is give you more notches in your frequency response. And I'm going to go downstairs and show you that on a plug-in instead, because it's a little bit easier to show you than building up this huge scary looking circuit. So here we are in Ableton. Just quickly, here's that loop. Heard it a lot. What we're going to do is I'm just going to put a phaser on here, and we're just going to go through this phaser. And so our phaser sounded something like this. Right, so that was with 1 notch in the frequency response, and we had this feedback we can muck about with. And you can hear how that deepens the phasing and kind of fattens up the mid-range a little bit. And we also, I actually forgot to show you this on my circuit, but it is in there, you'll see it in the schematic. I have this phase invert button where you can flip the phase of the phaser signal and mix it back in out of phase, and you get more of a band pass instead of that band notch effect, which sounds like this. Okay, so that is in there in the circuit. Have a look in the schematic and play around with that at home. So what we want to look at now is, how does adding more stages give us extra notches? I guess if we want 2 notches here, right, we can see now we've got 2 notches, and they're at different frequencies. So the original notch is now changed into these 2 notches either side. And so what's going on there? So when we've got 1 notch, right, remember we've got taking that frequency response, and we're taking the frequency at 90 degrees and doing it twice, and that gives us 180 degrees. So if we have 4 stages now, then what we've got is we're taking the frequencies at 45 degrees, and they're the ones, after we do it 45, 90, 135, 180, those frequencies are the ones that end up cancelling out. And going the other way, we've got 135, and then 135 again is 270, then again is 405, and then again is 540, which is 360, and which is back round to where in phase, and then another 180. So they end up effectively 180 degrees out as well. So it's a little bit subtle, that, and a little bit maybe confusing if you're not too keen on the maths. But essentially you can see graphically here, when we add another 2 stages, we get 2 separated like that. And if I add another one, they'll be like this. So you can see that first stage is now back. And if we add 4 and 5 and 6 and so on, and so we get these patterns of notches going out from the center frequency like this. And the more notches you have, the thicker the sound. So you saw there a good example of how feedback isn't always your friend. I mean, that's RuneScape. I mean, so that was quite cool, but that might not be what you want. So you do always have to be careful with that feedback. So what we can do is we can make as many notches as we want, and the more notches we have, the phasier it will sound, the thicker that phase will be. And we can also use feedback to make it phasier by taking the output and putting it back in the input. So we've already had that notch, and then we put it through the circuit again, and it makes that notch even deeper. You can experiment by changing slightly the values of the resistor and capacitor in the pair, and that will change how wide the notch is. So you can, if they're very well matched, you'll get a very narrow frequency, but if they're less well matched, you'll get a broader frequency notched out, and that will give you a different sound. For my patrons, we'll go over this in my design video, but if you're not a patron of mine, if you check out the schematic in the description, hopefully I've given you enough understanding that you'll be able to understand my design and adjust it for whatever your needs are. So as always, check out the description for schematics and simulation files and things like that. There's also a link to my Patreon. If you enjoy my videos, please consider supporting me on there so that you can help me make more. It's the best way you can support me if you're able, and it's somewhere you can find extra schematics, design videos, I answer patron questions and things like that. If you're not able to support me like that, then please share this video leave a like, leave a comment, make sure you subscribe, and most importantly, come back next time where there's lots more synthy goodness still to be had. And I'll see you then. Bye bye.